have size 3, 4, or 7? Is that no? How many ways can I pick k items out of it? So with that in mind, I'm going to draw here a little table, and I'm going to name it later, or you guys can name it for me. How stuff's looking like, here's n. If I have 0, I only get one possible value, because this is the empty set. If I have n equal 1, I get, here's k. So this is my table here. 0. If I pick 0, how many elements of 0, of size 0 I have? Of course, there's always going to be 1, right? There's only one element of, or one subset of size 0. This is the size of the big set, and this is, in how many ways can I pick a subset of that k? So I'm going to put here another k. If I have one element, in how many ways can I get something with one element? So in here, you can imagine this set being, this is a set of 1 things. In how many ways can I get 0 elements out of it? There's only one subset, right? Empty set. In how many ways can I get 1 element out of it?
2.
2 ways or 1 way?
2.
1.
There's only 1 way. It's that guy.
An empty set and
Right, total is 2, but there's one with 0 elements and one with 1 element. How about if I have 2 elements? In how many ways can I get 0? 2 elements, that is the set AB, right? Say, how many ways can I get 0 elements out of it? That's the empty set. It's always the empty set. In how many ways can I get 1 element out of it? 2. That's the set of A and B separately, right? And there's a possibility here for getting 2 elements, which is, of course, this last one, it's always 1, because the only way to get all the elements is to get the whole subset. It's only one possibility. How about if I have A, B, C? That will be 3 elements. In how many ways can I get 0? That's 1. In how many ways can I get 1 element out of it? 3, because I can get any set that's just 1 item. So there's 3 possible sets. The set of A, set of B, set of C. In how many ways can I get 2 elements out of it? That's subsets of how many? 2. So it's AB, AC, and BC. So that's 3. And then there's a way to get all of them, right? That's a 1. How about for 4? Like we said, this is always 1. There's only one subset of size 0. That's the empty set. How many subsets of size 1 are here? 4. How about of size 2? 6. How about of size 3? 4. And how about of size 4? 1. How about 5? How many subsets of size 0? 1. Of size 5? Of size 2? 10. Of size 3? 10. Of size 4? And of size 5? 1. Let's do one more. Size 6. I have how many elements of size, subsets of size 0? 1. Size 1, 6. 15, that's of size 2. We did this before when we checked all the pairs in a hexagon. Pairs in a hexagon, pairs of vertices in a hexagon corresponds to, think about the hexagon, right? How many vertices are there? 6. How many pairs, possible pairs I have? It'd be 6 choose 2. That would be 15 diagonals, 15 sides. And then how about 3? 20. How about 4? 15. And then 5? And then 1. That's 6. And of course, this keeps going. There's no surprise that this is a symmetric sequence of value, right? Wherever this 6 is here, it's going to be a 6 here, and there's a 4 here, there's going to be a 4 here. What's the reason for that? Yes.
N choose k is the same as n choose n minus k.
Right. The symmetry left, right comes from the fact that n choose k is the same as n choose n minus k. So choosing one item out of 6 is the same process of choosing 5 items out of 6. We said this last time. You can think of it the ones I take home versus leave in the store, or you can think the ones I leave in the stores and versus the one I take home. The way you think about it, the split into k versus n minus k is the same problem. Just formulate it. All right. So now I want to go back to that binomial theorem in a particular way. I want to say what happens when I think of x plus y, let's call it nice y, nice x plus y power 4. I'm going to use a little bit of recurrence or induction here to say this is x plus y times x plus y to the third, right? We all know that. Which suppose I already know. There was a formula for this, x plus y times, anybody remembers the formula for x plus y to the cube? What was it from last time? It was x cubed plus 3x squared y plus 3x y squared plus y cubed, right? So we already made a bunch of observations. All terms in this formula will have a bunch of x's and y's in them. And the sum of the exponents in every single term I get will be 4. Right? Be a bunch of x's and a bunch of y's, and the sum will be 4. In here is the same thing. If I expand this x plus y to the cube, all terms will be x's and y's. The sum of the exponents will be 3. Notice this is 3, 0, 2, 1, 1, 2, and 0, 3. So now I'm going to point out that this to me looks like a specific line in this triangle, in this table here. This line. See the coefficients? 1, 3, 3, 1. These are right here. 1, 3, 3, 1. And there's no surprise, this n here is of course n equal 3, which is the n equal 3 in here. My point is, in an induction sense, if we know this is 1, 3, 3, 1, what's going to happen when I multiply with another x plus y? I'm moving from n equal 3 to n equal 4, right? So this is n equal 4, which is 1n times n equal 3. What do you think is going to happen with those coefficients? They're going to end up being these ones here, right? Why is that? Let's do the multiplication. X times x cubed, x4, plus x times 3x squared y, 3x cubed y, right? I'm adding the next to these two, I'm making 3. Plus x times 3x squared y squared gives me what? 3x squared y squared plus x cubed x times y cubed, x times y cubed, right? Now we add the y, so that's just x multiplied with everybody. Let's add the y multiplied with everybody. I'm going to arrange them such that oranges goes with oranges. So whatever I get, x3y, I'm going to x cubed y, I'm going to arrange the same. So y times x cubed, where does this one go? Right here, right? It's, no, x cubed y. It's one of them, right? Plus y times 3x squared y is 3x cubed y cubed. Plus y times 3x y squared is 3x y cubed. Plus the last one, y times y cubed, y to the 4th. So now let's add up this whole thing. How many x4s do we have? 1 x4. Plus how many x cubed y's do we have? 4. 4x cubed y. Plus how many x squared y squared? 6x squared y squared. Plus how many xy cubes? 4xy cubes. Plus 1 y4. Did we get our coefficients? The next line?
Yes.
We did. Anybody knows how this table is called? Pascal triangle. Is the triangle of combination values. Any n choose k, it's sum in this triangle. The rows correspond to n and the columns correspond to k. Now, for this to be a proof, informally, we didn't start induction yet, but for this to work out all the time, not just in this example, right? Because I can multiply with another x plus y to get x plus y to the fifth to get to this line here. For this to work out, I'm only summing up some coefficients. This one here was the coefficient I had here. This 3, 3, 3, 1, and this the same row repeated 1, 3, 3, 1. So in some way, if you sum up this row with itself shifted, you're supposed to get the next row. Like in other words, see what happened here, what I did. I had 1, 3, 3, 1. I took the same row and I said, okay, 1, 3, 3, 1. And when I added up, I got what? 1, 4, 6, 4, 1. Would this process work the next row? If I shift this row by 1 and add it up to itself, would it work? Yeah. I don't know. 1, 4, 6, 4, 1. The same row. If I add it up, what do I get? 1, 5, 10, 10, 5, 1. Is that the one? Hmm. Who would have thoughts? How about again? 1, 5, 10, 5, what is it? Another 10, 5, 1. If I add it up, what do I get? 1, 6, 15, 20, 15. Damn. This one here. I mean, if this is true, clearly this is going to work out, right? Because what's going to happen when you multiply with another x plus y? You're just going to get that row first when you this is 1 and 1, right? It's always 1 and 1. 1 times everybody will give you whatever you had, that row. 1 times everybody will give you again that shifted. So then when you add up oranges with oranges, apples with apples, grapefruits with grapefruits, you get that row summed up. Would that be the next row? That will prove the binomial theorem, right? If we can somehow argue that this is a phenomenon that happens all the time with combinations, that will prove binomial theorem in general, assuming we know induction, because we have to multiply with x plus y to get to the next end, right? And again, x plus y is against them. We'll get to induction. But I think everybody can see that this relies on the fact that a row shifted and added to itself from this table gives me the next row, which I know are the binomial coefficients. Why is this true then? Can we formulate this not with examples, but with the general form? What needs to add to what? When I say 4 plus 6 equals 10, who was this 6 in terms of combinations? This 6 was who? 4 choose 2. And who was this 4? 4 choose 1. And what am I supposed to get?
5 choose
5 choose 2, right? How about in here? Say, who was this 5? This is 5 choose 4 plus 5 choose 3. And you're supposed to get, who is this? 6 choose 4. And you can run multiple examples of what does it mean to add a row to itself in that way to get the next one. Can we formulate this property in general? Because this is a property we want. We saw it in the example. Seems to work out. But what is the general property in terms of n and k, for any n and every k? What are we saying? N choose k, or plus n choose k minus 1, supposed to be n plus 1 choose k. I think this is the general formula that actually, if you replace n and k with different values, you get all these additions, right? In fact, if you think of the shifting stuff. When I shift a row by 1, it's what was k becomes k minus 1, or the other way, what was k minus 1 becomes k. So I'm adding the two values consecutive in that row effectively. And I'm supposed to get the next row at column k. Who's with me so far? So this is a hypothesis. Is this true? I mean, we would like to be true, because if this is true, then the rows work out the addition, and if the addition works out, we just prove binomial theorem. But this is speculation so far. Is it always true for any n and k? I mean, if it is, we have to prove it. If it's not, we have to show a counterexample. Which one is it? Well, we believe it's true, right? It seems too nice, too fitting with everything to not be true, right? It works with the table, it works with the binomial theorem, makes total sense. But then how do we prove it?
Is n choose a negative number to solve?
Not now. we don't want to choose -3 elements. Let's just say they're naturals, okay? Later on, not in this course, maybe they'll be defined. So for now, k and n have to be natural numbers, and k has to be at most n. Because you can't pick more than 100 students for a class of 100 students. Or if you really try, the number of ways to do that is 0. Right? So let's say for negative numbers, or for k bigger than n, it's 0. So this, I think her point is, for this to make sense, k has to be at least 1. Because if k is not 1, then this is a negative value. What does that mean? And n has to be bigger than k. Right? At least k. So why is this true? Again, what are we doing here? If this is true, the table works that way. Take any line, shift it by 1, add it to itself, you get the next line, which means this works that way. It means the coefficients for these values in the binomial expansion, this is the binomial and this is the expansion, will always be the n choose k values. So let me try a proof here. I'm going to look at this guy and say, who's n plus 1 choose k? Is a way, number of ways to pick k out of n plus 1 items. Here are the items. Item 1, item 2, up to out, n, and item n plus 1. Now, there's a set. Items, those items have ID. There's student 1, student 2, they have a name. But the order is not important. I just choose an order to write them on the board here. I don't treat this as a sequence. It's a set, but I know who's in the set, right? When I say A, B, C, I know who's A, who's B, who's C. The order, I can write it in any order I want. Whether I write A, B, C, or B, C, A, or B, A, C, it's the same set. Same thing in here. There's no order, just items have IDs. And I want, in how many ways I want to pick, I can pick K. So I'm going to pick K now. But this number of ways, I'm going to use the sum rule. I'm going to split those ways into 2 major classes of ways. And to apply the sum rule, what do I need for these 2 sets of cases or 2 classes? Yes?
They have to be disjoint.
They have to be disjoint. So I'm going to separate. There are ways to do that, and there are ways to do that, the number of ways being not intersecting at all. So remember, I have to pick k items. So here's my 2 classes. All the k items, subsets, including item n plus 1. So that's some subsets of k that include this last guy. And k items subsets, how do I say something to make sure they're disjoint? Like, be no questions asked about being disjoint. if I say these are all the subsets that include the last item, what I need to put here to make sure they are absolutely disjoint without any further explanation. Yes?
Subsets that do not include last item?
Do not include n plus 1. Is it clear they are disjoint? These ways of picking it will end up with that item in, and these other ways of picking them will end up with that item out. There's no one way that can be in both sides, right? Because in one side includes, you know, Halloween, in the other side does not include Halloween. Those are two different things. Now, the other thing I need to be worried about is all the problems that I split with sum rule or the inclusion exclusion is I'm covering everything. Is there any way to pick k items that is neither here or here? Did I miss anything? So one thing is the disjoint part, and I think we all can agree those cannot result in the same k item set. But did I miss anything? Is there any k subset that's not here and not here, so I missed it? Is there? Or is this covering everything? It's saying if you pick k item subset from a set of n plus 1 things, you gotta be either in this side or in this side. And you can't be in both, and you have to be in one of them. Agree? Hands up. So now, how many ways to pick subsets including n plus 1? How can I think of that? So n plus 1 is in. This subset that is generating here will have n plus 1 in it, guaranteed. And then it has to have how many others? If n plus 1 is guaranteed to be in, and my subset has size k total, how many other items are there? K minus 1 items. From what set taken? So this is a set of k minus 1 items. Again, this does include n plus 1, because that's why I said here, n plus 1, the last element has to be in this subset. Now what about the rest of the subset? How much is the rest? K minus 1, right? Because the whole set is k subset, and this is one of them. So these k minus 1 items are from what set? Yes.
The set of n items that are.
Which n? 1 to n. Because n plus 1 is already taken, so the other k minus 1 items have to be from 1 to n. So how many ways that? How many ways can I generate this k minus 1 subset, excluding n plus 1, from n elements?
And choose k minus 1.
That's n choose k minus 1. Because it comes down to picking k minus 1 items out of a set of n. And any set combined to this element n plus 1 will give me a valid subset. How about this? This one excludes item n plus 1. So n plus 1 item is not here. Therefore, how many items I have to have there? This is a subset of k items, so there's gotta be k items out of which set I can take those k items?
N.
The same set like before, right? Because n plus 1 is not allowed in this case. So it's 1, 2, up to n. In how many ways can I get k items out of n? N choose k. So if I apply the sum rule, because those two sets are disjoint, I get that this count, that's all the ways that include n plus 1, plus this count, that's all the ways that do not include n plus 1, will give me this count, which is all the ways to include k items from 1 to n plus 1, right? The sum rule would say these are two sets, A and B, and because they're disjoint, the size of this guy plus the size of this guy has to be n by k plus 1, right? But now we already computed that this is n choose k minus 1 plus n choose k. So this is a proof of this also called Pascal formula or equation. That's the generating formula for this table. Yes?
Just to clarify, when two sets are disjoint, it means that they share none of the same vertices, right?
None of the same elements. So the sets here are the ways to pick k elements. So it's either all the set in here is a set of subsets. These are all subsets that include n plus 1. And these are all the subsets that do not include n plus 1. Therefore, they cannot have common subsets between them. So let's instantiate this in an example to make it less abstract. Yes?
Is it n plus 1 over k or n over k plus 1?
Here?
Yeah.
So this is not over like in a fraction. It's a n.
Yeah, like n choose k plus 1 or n plus 1 choose k.
It's n plus 1. You're right. N plus 1 choose k. Is this one here? Sorry. Let's instantiate it with an actual problem. I have n equal 5, so the set is A, B, C, D, E. And I have k equal 3. Let's say n plus 1 equal 5. So then the formula says 5 choose 3 has to be 4 choose 3 plus 4 choose 2, right? That's what the formula says. In other words, if you want to pick subsets of 3, you can choose subsets of 3 out of 4 and subsets of 2 out of 4. So we're going to do the same thing. We're going to do this split. This splits into subsets that include the last one, E. Right? So what are the subsets of 3 that include E? Well, that means there are subsets of 2 out of A, B, C, D plus E. Because if I want a subset of 3 elements that includes E, comes down to getting 2 elements from the rest and E. So which ones are those? A, B, E, A, C, E, A, D, E, B, C, E, B, D, E, C, D, E. Is that true? So this is counting the first part, all subsets including the last one. Because I have 3 total, the last one is counts as one of the 3. I need now all the subsets from the previous 4 without E. That's A, B, A, C, A, D, B, C, B, D, and C, D. And I add E to everybody. And the other branch of the sum rule is subsets of how many? 3 without E's. So now I have to pick 3 elements, but I'm not allowed to pick E. Which are the subsets that contain 3 elements but not E? A, B, C. Who else? A, B, D. B, C, D. A, C, D. Not surprised that this is in how many ways I can choose the first 2 out of 4. So that's 4 choose 2, which is 6. And this is in how many ways I can choose all 3 out of 4. That's 4 choose 3, which is 4. So now if I apply the sum rule, I should get that 6 plus 4, and this should be 10. So that's just an instantiation of how the proof actually works. All right. So now that this is true, we prove binomial theorem, we have Pascal triangle, we have Pascal formula. Let's try some x and y and see what happens. There's some interesting x and y's that we can put in here. So there's some very obvious cases. What happens if I put x equal 1 and y equal 1? The actual formula in general, we said last time, it's x plus y at n is the sum from k equals 0 to n of n choose k. That's the coefficient. X to the k, y n minus k. We can write it, sometimes it's written the other way, don't get confused, it means the same exact thing. K equals 0 to n choose k, x at n minus k, y at k. This is the same thing due to the fact that n choose k is the same as n choose n minus k. Is the x at k will have the same exact coefficient in here and here, right? How this formula look for x equal 1 and y equal 1? I get 1 plus 1 at n is the sum of k equals 0 to n choose k times 1 to the k times 1 n minus k. I'm just mechanically replacing here x with 1 and y with 1. So what do I do? What do I get? 1 at the power and 1 at the power, they both 1. So it's just the sum from k equals 0 to n of n choose k, which if I am to write it down, would be n choose 0 plus n choose 1 plus n choose 2 plus n choose n. And this guy in here, if I am to write it down, is 2 to the n, right? 1 plus 1, 2 to the n. You guys seen this formula already. 2 to the n is this sum. Can anybody point me out where have we seen that formula already? It was not written that way, but it was exactly the same thing. Yes?
Power sets?
Power sets. This was what? The size of the power set?
Yeah,
And what are those?
the size of subsets of size k.
Right, this is how many subsets have size 0, how many subsets have size 1, how many subsets have size 2, up to how many subsets have size n. So if you agree with me that those are disjoint, because any subset can either have 1 or 2 or 3 or 4 elements, right? Then I can sum them up and get the count of all the subsets, which is the power set, which I know is 2 to the n. This is the size of power set. Of set with size n. So again, what is this? How many subsets have size 0? It's only 1, the empty set. How many subsets have size 1? That's n, because I can pick one element at a time to get the subset out of it. How many subsets have size n? That's only 1, is the whole set. But if you add them up together, you get the counts for all subsets, which we already know is 2 to the n. Here's another example. What happens if I plug it in there, 1 and minus 1? So let's try that. I'm making x equal 1, y equal minus 1. So I get 1 plus minus 1 at power n is sum from k equals 0 to n of n choose k. X is 1, so that's 1 to the k, times minus 1 to n minus k. How much is this if I really am to write it down without the sum, just one by one? So we can do that. The first one is what? N choose 0, right? With what sign? The 1 is always 1, so I don't have to worry about this one. But what sign is this? Minus 1 at n. That I have to leave alone because I don't know how minus 1 works. Minus 1 at every even power is 1. And minus 1 at every odd power is negative 1. So the 1 at k generates only once. It's like, I'm not going to write that one down. But this one generates sometimes 1, sometimes a minus 1 alternatively, right? Because for after every even comes an odd, and after every odd comes an even. So the next one is minus 1 at n minus 1, and choose 1, plus minus 1 at n minus 2, and choose 2, plus, by the time I get to n, choose n minus 1, what is the sign of this? This is minus 1 at what power? So there's the last two coefficients here, n choose n minus 1 and n choose n. What's the exponent in there?
1.
In here is 1 and here is
0.
0. Now I can, the same formula, I can write it like I said here, I can write it backwards to the exponents. Maybe that's more easy to see. K equals 0 and n choose k, 1 at n minus k, minus 1 at k. Due to the symmetry of k and n minus k, this is the same quantity. So now the first one I know for sure it's n choose 0. That's with a plus, right? Because when k is 0, I get 1 at n, that's 1. Minus 1 at 0, that's n choose 0. That's a plus. Minus n choose 1. Because for n choose 1, k is equal 1 here. 1, this 1 doesn't matter, but minus 1 at 1 will give the minus in the front. Plus n choose 2, minus n choose 3, plus so on and so forth. And then I'm going to have some minus 1s in here for the last one. This is just the basics of some equalities with combinatorics. There's a lot more such equalities, but how to manipulate the combinatorials to get an equation out of that. Now, of course, I can also compute the left side. How much is this?
0.
That's 0. So that will tell me that the guys that have plus, if you sum them up, have to have the same sum as the guys that have minus, right? Because I can rewrite this equation to say everybody that has a minus goes on the other side, and now the sum of them have to be the sum of the ones that have plus. So I can write it like n choose 1 plus n choose 3 plus n choose 5 plus da 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 is equal to n choose 0 plus n choose 2 plus n choose 4 plus da da da. Up to where it ends. Same thing, just moving one to another. So we'll do a bunch of exercises in the second half of this lecture, just basic stuff. And we'll do more exercises tomorrow and Thursday at recitation, counting problems. Before we do so, before we go into exercises, I want to show you one use of this binomial theorem here. Particularly this formula here that I've got, very precious to me. I'm going to use it in a proof. So now I want to make a proof that's going to use this formula. A proof that we need anyway, so it's good we got here now, so we can make this proof. The proof is the inclusion-exclusion formula. For n sets. So let's remember a little bit how it worked with, say, 4 sets. Was A union B union C union D. That was what? A plus B plus C plus D minus, anybody remembers? Subtract intersections of 2. Subtract meaning because these guys are overcounted. What are the intersections of 2? A intersect C, A intersect D, B intersect C, B intersect D, and C intersect D. Then was putting back intersections of 3. The reason being, every element in intersections of 3 has been added 3 times and subtracted 3 times, so I need to put it back. So A intersect B intersect C plus A intersect C intersect D plus A intersect B intersect D plus B intersect C intersect D. Now I have another problem that elements common to all 4 have been added 4 times, subtracted 6 times, right? Added back 4 times. So what's the count now? I added it 4 times. Something that's in all 4 sets. It's added 4 times, subtracted 6 times, added back 4 times. Total count? So if an element is in all 4 sets, I've added it 4 times in here. I've taken out 6 times because it's in all intersections of 2. I put it back 4 times. Total count so far is what for that one element? 2. So I need to take it out once. A intersect B intersect C intersect D. So that's for 4 sets. How does it look for n sets? Just let's see the best we can do here. Size of the union of A sets up to A n minus 1 and A n is, how can we write this down? Sum for every I of the size of AI, that's the plus each set, right? A, B, C, D. We have to subtract for every I different than J, so for every pair, we subtract what? The size of? How do I write this line here in general to say for all pairs of 2 sets, subtract the size of the intersection? What do I have to write here? Well, all the pairs are generated by the sum that goes over all pairs. This is IJ pair. What do I write inside to get all these guys? It's written in concise form. Instead of enumerating all pairs, I'm going to just write something, yes, inside the sum. AI intersect AJ. Now, say I is 1 and J is 2. This would correspond to what? A1 intersect A2. And if I is 1 and J is 3, this corresponds to A1 intersect A3. But do I want this listed both ways? I want to subtract A1 intersect A2 and then later on A2 intersect A1, or just once?
Just once.
So how do I make this sum to say I only want it once, not twice? Can I specify something in the indexing here in IJ to say I only want it once? Because otherwise it'd be 2, 3, and 3, 2 appears twice as a pair. Yes?
Just say that I is always S and J.
I can say that. Now, 1, 2 will be part of this sum, but 2, 1 is not part of this sum because I'm specifying I has to be small. So I don't want to see twice. Now, how do I put back all the intersections of 3? So plus sum of what? I smaller than J smaller than K of who? All the triplets. So that's AI intersect AJ intersect AK. Then I have to take down intersections of 4. This is I smaller than J smaller than K smaller than L. AI intersect AJ intersect AK intersect AL. Again, I'm putting them in a particular order because I want that intersection A1, A2, A3, A4, or A3, A4, A6, A7 to only appear once in my summation. I don't want all the permutations of those indices because the intersection, I only care about it once. Now I'm going to put a bunch of dots, as in it's up to your imagination what comes next. And the last one will be what? This is a -1 at some power, right? Because it's plus, minus, plus, minus, plus, minus, plus, minus. We know which one is the last intersection. Is what? It's only one, right? Let's write down the last one. Will be -1 at some power, and it will be what? A1 intersect with A2 intersect with AN. That's all of them. So the power will be
To the end.
N. Can we write the general term in here? So instead of these dots, if I say this is the size of one set, this is intersections of 2, this is intersections of 3 that are put back with plus. So the reason this is plus is because this is what? I think it's n plus 1 here, by the way. It's plus, it's -1 at 2, right? This is -1 at 3. So it's, see, the count of the sets is not identical with the exponent here. So when I have n sets, I need this to be not n, but the other one. How can I write the general term in here? So if I want the intersections of k sets, it will be -1 at some power, sum over all I1, I2, smaller than up to Ik. Now I have intersecting k things, and this will be the intersection of I1 intersect I2 intersect this up to Ik. So this is saying take all the intersections of k sets only once, because these are in a particular order, and then this would be probably -1 at k plus 1. If I have 3 sets, it's going to be a plus. If I have 4 sets, it's going to be a minus, so on and so forth. That's the general formula for inclusion-exclusion principle. It works for any number of sets, 2, 3, 4, 6, 10, doesn't matter. That's what we want to prove, that formula. We want to prove the general case, not just for 3 or 4 sets. Just the here, here, k plus 1. Because you notice that the number of sets 2 doesn't match the -1. Whenever I have 2, I need a minus, which is -1 at what kind of power? Odd. And when I have 3, I need -1 at. So I can put 2 or 4 here. It won't matter because it's only even versus odd. So when I have k things, the sign will be given by -1 at k plus 1, or k minus 1 is the same, but not k. Who's with me on at least what are we trying to prove here? Hands up so I can see them, please. Okay. How can we prove this thing in general? One possibility will be induction, right? If this formula works for n sets, how do you make it work for n plus 1 sets? But we won't do that today because we didn't study induction. When we do induction, we'll redo this proof by induction. What we want to do is proof by counting. So while the formula is a little scary in there, the proof is not scary at all. So the proof is very easy once you understand what it's trying to do. So proof by counting. Let's say element X is part of M sets and not part of the other how many sets I have total? N minus n sets. Right? So I'm saying, let's pick an element. Remember, those are sets. Those are this A, B, C, and D. And now I'm picking an element. An element is a dot. Is one of those. And how many elements is this dot here? How many sets contain that dot? One set. How about this dot? Two sets. How about this dot? How about this dot here? All of them. How about this one here?
3.
So you look at this, all these elements in the union, any element that's part in here, and you know in how many sets that element is part of. So let's pick some generic element and a generic number of sets. Any element will be part of some sets. Could be 1, 2, 3, maybe all of them. Let's assume those elements are A1, A2, up to AM. You could say, hey, you can't be that lucky. You pick an element, it's in 3 sets, gotta be exactly ABC. How do you know that? This is just a matter of re-IDing these sets. I pick an element, is in M sets. I can call those M sets A1, A2, up to AM, and call the other sets the rest, right? Just reordering the IDs of the sets. It doesn't restrict me in any way. It's not like I'm picking a special X. It's a generic X, and I'm calling the sets that this X belongs to the first M sets. And if it's one set, M is 1. If it's 2 sets, M will be 2. If it's all sets, M will be N. Now I want to go over this formula and see how many times I've counted X. So now I'm going to go back to the inclusion, exclusion formula and count X. Like how many times I've counted X. I go line by line. When I say sum, the first line, sum of I, right, of all AI. That's the first line in here, right? How many times X got been counted when I say this?
A, M.
How many of those contain M in them? Right? This is all N of them, but only M of those sets contain X, and the other N minus M do not contain X. So how many times X has been counted in here? Right? This is M sets with X. So the count is plus M. Plus because there's a plus in front of it. Now I go back to take out intersections of 2, right? The next line. It's minus sum over all pairs AI intersect AJ. How many of these pairs contain X? So X is in M sets, not all of them. How many pairs contain X in them? Pairs AI intersect AJ contain X. How many? So these intersections are all possible intersections, which are how many intersections, by the way? If I have n sets, how many intersections of 2 get? How many terms are in here? N choose 2, right? But not all these terms contain X, because X appears only when both sets contain X, right? It's an intersection, so to have X in there, it's only the intersections of sets that contain X here and here. So how many of those intersections contain X?
M choose.
M choose 2. Maybe it sounds very simple, and it is. It's saying, well, some of those intersections are not of the sets A1, A2 up to AM, so they do not contain X. Out of the A1, A2 up to AM, all pairs of them will contain X, because X is in both sets, so it'll be in the intersection. Again, what is this? Is any AI intersect AJ with what property? I smaller than j, smaller or equal than m. All the intersections of two sets from only this side, because the other sets are a n plus 1, a n plus 2, and a n. Those contain x. Those do not contain x. So every time I do an intersection of pair, if both sets are from here, I get x in the intersection. If I intersect 2 from here, I don't get x. And if I intersect 1 from here or 1 from here, I get x or not? No, because intersection, you must be on both sides to be in the intersection. So only the pairs of sets from here give me x, which are exactly m choose 2. So the count, what happened to the count here?
Minus M choose 2.
It's minus m choose 2. How about the next guy? I want all the triplets, a smaller than j smaller than k, that contain in the intersection. How many of these triplets will contain x? Yeah, m choose 3, right? M choose 3. Intersections of 3 contain x. Again, what I'm doing here, I'm only counting x, not the other elements. X is one element. I'm saying how many times you put it with plus, how many times you put it with minus, how many times you put it with plus again. So now what happens to my count? That increased by m plus 3. So you can see where this is going. What happened in that last line with k? So in a generic line, I have sum of I1 smaller than I2 smaller than ik. This is the generic one. Intersection of k sets. How many intersections of k sets contain x? Well, if k happens to be more than m, how many?
M choose M.
What I'm saying is I'm intersecting k sets. K could be 20. If this k is more than m sets, would I get x in there? Why not? Yes.
Because x is only in m sets, so if you add another one, x isn't going to be in
Any set of any intersection of more than m must contain a set from the other side, guaranteed, right? Because it's more than m. So if it contains any set from the other side, there's no x in there. Who's with me? It's not too bad. So the count is, what happens to the count? If k is bigger than m, 0, there is no x. I'm not subtracting any x. X is not in that intersection. What happens if k is smaller than m? What happens to the count? It's just what happens to 2 and 3. In how many ways can I get the intersections of k out of m? So that would be m choose k with what sign? Minus 1 at, say, k plus 1. It's not k. See, when it's 3, it's a plus. When it's 2, it's a minus. So this one will be minus 1 at k plus 1 when it's k. But this whole thing goes up to intersections of m, right? This was what this is telling us is that as soon as you intersect more than m sets, no more x's. You don't get to change the counts at all because x is not in those intersections. So now if we get to total count, what do we have? M minus total count for element x. M minus m choose 2 plus m choose 3 minus m choose 4. And the last one will be what? M choose m, right? Because the last k is m. We just said if k starts being bigger than m in my formula, count of x is not affected. There's no more x's. The only thing is, what is the sign here? M plus 1? How many people follow me? So let's say this again. This is the count from individual sets. This is subtracting intersections of 2 that contain x, adding intersections of all 3 that contain x, subtracting intersections of 4, so on and so forth, up to m. The formula goes further than m. But further than m, there's no more x's to add or subtract, so we don't have to worry about that. All those counts after, when k becomes bigger than m, count will be 0. Yes?
Why is there a plus in the bottom one? Because do we not know if it's going to be a plus or
Right, so it's -1 at k plus 1? Correct. So how much is all this? Do we know the answer to that? Let's look in here.
Oh, what is it?
Is that, how close is this to this formula right here?
Same?
This is a mistake, this is not n here, right?
Yeah, that's fine.
N plus 1. So it's almost the same, but it starts where? This one starts at n0, which is how much is n choose 0? 1. That one doesn't start at 1. So do I have every single term except the first one? In this formula, this is for m, this is for n. I have all the ones in here. Oh wait, this I think was correct n. Was it n or n plus 1 in here? This in here was n. Is that correct or incorrect? I think that's correct.
Yeah.
So what happens to this formula? There's two differences. Let's look again at the formulas. The other formula was, let's write it in terms of m. It's m choose 0, right? Minus m choose 1 plus m choose 2. That formula in there. The last one is plus -1 at m choose m. And we know this whole thing is equal with 0. So now, what's the difference between these two formulas? They're almost identical. First of all, this one here is missing a term. Which term? It's missing this term, right? Because this corresponds to that. This is this. This will be the next one. It's what's the next one? Minus m choose 3, right? And the last one is the last one. So the other difference is, except for this, is that the signs were backwards. This is minus, this is plus, plus, minus, minus, plus, and so on and so forth. So how much this quantity needs to be, if I call this quantity, let's say t, big T, I got m choose 0 minus t, because I'm reversing the sign, has to be 0. Right? This in here, it's minus t, is the whole formula with the sign reversed. So I get this minus t equals 0, which means how much is t?
1.
T is 1. Is that proving inclusion-exclusion principle? I think it does. It says the count in this formula for x, after you do all these subtractions of 2, additions of 3, what, is 1. Isn't that what we want, to count every element exactly once? So the count for x is 1, which means my formula counts every element in the union once, which is what I want. How do we feel about this? It's an honor thing, this proof, right? The proof, it's not that complicated once you understand what it does. It counts, it go through the whole formula. It says, pick any element you want, x. It's going to be in some sets, maybe 1 set, maybe 2 sets, maybe 3 sets, maybe 5 sets, maybe all the sets. How many times you counted addition and subtracted? So you go by how many times I counted here, that many times. Subtracted, that many times. Added back, that many times. Subtracted again, that many times. You add up all those counts and you get 1, which means you counted correctly, because that's your purpose, to count every element once. So that x was a random element in the union. This counting technique works for every single element. Therefore, in this whole summation here, everybody is counted exactly once. So this number gotta be the size of the union, because everything is counted exactly once. So let's do some problems now. Practice problems. This practice problem is what the other sections did for 2 lectures. So we'll try to do it in half an hour. Let's see where to start. I want to distribute 3 $1.20 bills to 10 people. Obviously, most of those people will get no money. Right? How many ways can I do that? In general, I'm not going to state how many ways. Every counting problem says distribute something among people, effectively, implicitly asking how many ways can you do it. So the first question when we ask an accounting problem is, who has IDs here? The bills have IDs? Do I have 3 bills of 20? Are they identical, or they bill 1, bill 2, and bill 3? Identical. So the bills don't have ID. They're like candies. They're the same. How about the people? Person 1 to 10. Do they have IDs? Is person 1 different than person 2 than person 3? Yes. So how do we count this? I apply the sum rule. I want to distinguish possibilities into these joint cases. So I have several cases. Each person gets at most 1 bill. So a person can get a bill or not get a bill, but if you get a bill, you get only 1. What this comes down to? How many ways? How many people will get bills in this way? 3, right? Out of 10. So it comes down to choosing the 3 people that get bills out of 10. Then another case is 1 person gets 2 bills and 1 gets 1 bill. Is that a disjoint case with this one? Yes. So how many ways 1 gets 2 and 1 gets 1? I have to pick the ones that get 2. That's the people who get 2 bills. Is that? No, that's wrong. It's what? Then choose 1, right? Choose 1 person that gets 2 bills. And then I have more choices. Once I give 2 bills to some person, I still have to give the remaining bill to one of the, how many are other people? That's 9, choose 1, right? Choose 1 out of 9. And there's one more case, of course, which is 1 person gets all 3 bills. How many ways are to do that? We choose 1 out of 10, right? Are those disjoint cases? These are all the ways to allocate 3 bills, and I didn't count everything twice because none of these ways are intersecting the other cases. So then I just sum this up. I won't say what it is, we'll just sum it up. Again, sum rule, I have to be careful of 2 things on sum rule. Make sure you didn't miss anything. Is there any way to distribute bills that are not one of these 3? No. Am I really running disjoint cases here? Do I have any intersection? No. Therefore, I apply the sum rule. Sum of the counts, I get the value. We'll get back in a little bit to this problem, but before that, let's do a few more. Not this. I'm looking for something else. This might be this one here. All right. So that's example 1. Example 2. 10-person race assign medals. What are the medals? Gold, silver, bronze. What is this? Obviously, out of 10 people, how many will get medals? Does the order of the 3 matters or not? Is it a set of 3 or a sequence of 3?
Sequence.
Ranking, if you don't like sequence, you can say ranking or order, whatever. It's not a set. It's not like we're asking you, who are the 3 people that get medals? We say, who's got gold, who's got silver, who's got bronze. So, what is this?
10 times 9 times.
It's the P R permutation of out of 10, get 3. Anybody remembers the formula for that? Yes. Divide by? It's 3 factorial or 7 factorial? That's a useful information to have in a quiz. So you don't, quizzes are mostly white or black. You do a mistake like that, boom. Nah, it's not like that bad, but you gotta get those right. I could have, that's an obvious answer because it's formulated like the formula. How can I think in terms of combinations? I can choose first the set of 3 medals out of order, without order. In how many ways can I pick 3 medalists out of 10? 10 choose 3. But then, once I got the 3 guys that get the medals, what do? I can sort them in who gets gold, who gets bronze. So this is now, then permute them, the 3 for medals. G, S, bronze. So how many ways can I permute 3 items? That's 3 factorial. So the answer will be 10 choose 3 times 3 factorial. That's 10 factorial, 3 factorial, 7 factorial, times 3 factorial. This goes away. I get 10 factorial divided by 7 factorial. Same answer. That's actually how we proved this formula, if you remember. We were saying, so all the permutations multiply, you get the set. Let's do another. This is identical problem. Just going to mention here 10 Star Wars movies. There really that many? Watch 4 of them in order with friends. So friends in here can disagree about which 4 are the best 4 Star Wars movies. And once you agree on which 4 to watch, you can again disagree on the order in which to watch. It's a good question because the first Star Wars movies, well, actually, they say it was not the first one, right? We started the episode 4. So it's a legitimate disagreement. If you watch a bunch of them, do you start from 1 or from 4? Anyway, what's the answer here? I have to choose 10, 4, but is it a combination or a permutation? It's an R permutation, so this is 10 factorial divided by 6 factorial. Because I don't just pick the movies, I pick the order in which to watch them. Every time the collection that you pick has some special role, first, second, third, CEO, CTO, legal officer, you know, play basketball, I'm looking for a center, a guard, you know, and the other roles in the team. Every time this is named means the order matters. Every time it's not named, I'm just looking for 5 players. It means I'm looking for a set. When I name the order, which movie goes first, second, third, then I'm looking for an order. What else we can do here? Here's another one. Example number 4. Choose 4 students from 100 to form committee. Do I specify who's the head of the committee, Who's the junior, who's the senior, anything like that? No. So I'm looking for what? A set. So the answer is 100 choose 4, which of course is 100 times 4 factorial times 96 factorial. Five. Five card hands from deck. How many cards are in the card deck? 52. Say it like that. Do I put it in an order? Is there any order? I'm asking for a set of 5. So the answer is 52. Choose 5. What if I say two card hands, both jack or better? You have to know the order of cards. Jack or better means what? A deck of cards have how many suits? 4 suits. In each suit, what means jack or better? Jack, queen, king, ace. So what are the possible 2 card hands that include only jacks or better in both? I'm still looking for a set, right? I'm not talking about the order. It's not a first card and a second card, but I'm not choosing out of all 52 cards anymore. I'm choosing out of how many? 16. There's 16 cards that are better than jacks or equal. So then the answer is 16 choose 2. Because I'm choosing 2 cards out of not all 52, but 16 of them. Example number 7. 250 students choose 5 for football and 5 for basketball. How many ways can I make the 2 teams, the football team and the basketball team? Yes.
You have overlapping players.
No. No overlap. How do I do this?
250, choose 5 plus 240.
So I can choose 250. He's saying choose first one of the teams. Let's say 7 people play football to be not confusing this. I choose that team, and then
You choose the
that's
other
done.
team from
What do I have to do now?
let's
Is
choose
it
the
multiply
second
or
team.
addition here?
Addition.
Oh, let's figure out of what. So now I have to choose the other team. Out of what? How many out of how many?
243.
243, because the 7 ones are going to play football. So I only have 243. Choose 5. And now what is in between those 2 quantities? Is it for every way to pick 7 play football, I get that many ways to play the basketball team? If that will be true, what's the sign in there? For every choice of the football team, there's so many choices of the basketball team. That will mean multiplication. If I say this number of ways, to get addition, it really has to correspond to a sum rule, right? Is it really that many ways to form the 2 teams plus that many ways to form the 2 teams? Yes.
Would we get a different answer if we chose basketball players first?
So first of all, what's the answer? Multiplication. It's not a sum rule. It's for each possibility here. I have that many possibilities. They're dependent because those 243 depends of which 7 you pick. But nevertheless, for each possibility in here, I have that many possibilities for the basketball team. He's saying, what if I pick first the basketball team, and then will be 245 choose 7, right? Is that the same answer? Anybody factorials? Help me out here. You can't really do factorials with a calculator. What's the reason for that? They're way bigger than the calculator can do, any calculator. So we can't do factorials with calculator. But maybe if we write out those factorials, should they be the same number or not? Yes. They should be. So you can verify by canceling factorials out, see if you get the same answer or not. I think you should. There's more examples. Playlist of songs. 5 Beatles out of 10 and 7. I can't read these names. Never heard of this band, did you? Heard of this band? Somebody wrote this problem here just to put me into the tight spot. I never heard of this band, but presumably it's a nice band. I heard of Beatles. I like Beatles. I have them on my iTunes, you know, but not this band. Out of, say I have 13. So my playlist has size 12, and I want to have exactly that combination of 5 Beatles and 7 Pomplamoose songs, right? Playlist sounds like what to you? Sounds like in order or out of order? Out of order or in order? When you say playlist, if the DJ has a good playlist, are you counting what songs come after what songs or not? Usually when people make the DJs good, it means the sequence of playing songs is good. I don't go to clubs that often. Do you? When you say the DJ is good, don't you mean that after that song comes a nice song that matches the other one? That means order. Okay, so here's my playlist. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the song 1, song 2, song 3, up to song 12. How do I think of this? I have 10 options for Beatles and 13 songs from the other band, and I have to put them in an order. How? Well, so I have to make few choices. Think about the choices you make. I can choose first the Beatles songs. How many ways can I choose 5 songs out of 10 as a set, out of order? How many? Then choose 5. Then I can choose the other band songs out of order. So choose B 5 songs, choose P 7 songs. So this will be how many? 13 choose 7. And then I can say, now I've got how many songs? 12 songs, but I have to permute them. Always. So, what would be the answer if I think about this way? 10 choose 5, choose the songs. 13 choose 7, choose the other band songs. And then 12 factorial. Is that correct? No. Here's another way to think about this problem. I don't know if it's correct. That's your job to figure out if it's correct. Honestly, I'm saying some things might be wrong, and the way you made mistakes, we made mistakes the same way. Here's another way to think about the same exact problem. I'm going to choose spots in the playlist for Beatles songs. So I have this playlist here. How many spots are in it? 12. In how many ways can I choose where the Beatles songs go? As in, here's Beatles song, Beatles song, Beatles song, Beatles songs, and Beatles songs. How many ways can I do that? That's 12 choose 5. Because it choose 5 spots out of 12. You don't get to choose the order. The order is fixed the playlist order. So you can choose the order. You just choose which spots get into Beatles songs. And then I do what? Do I still choose spots for P songs? Why not? It's whatever's remaining. There's no way to choose spots in here. Whatever's not a Beatles song, gotta be that song, right? So that's no choice. But now, I have to choose the Beatles songs. So I have the spots. These are the Beatles song spots. In how many ways can I choose the Beatles songs that go in there? So I have the spots, but I have to choose the songs, the actual songs that go. So is that choosing in order or out of order? In order. And how many I choose? I choose the 5 songs out of, I have 10 songs, and I have to choose 5 of them in order. The order matters. The same 5 in a different order will be a different playlist. So then I choose here the P songs. In how many ways? The positions are fixed, or the spots, because it's whatever remaining from the Beatles songs. In how many ways can I choose the songs now? It's in order. So out of 13 songs, I have to choose 7. So think about this way. I get 12 choose 5 times, how much is this? 10 factorial by 5 factorial times 13 factorial by 6 factorial. Let's replace this. 12 factorial, 12 choose 5 is what? 5 factorial times 7 factorial. How much we get in here? How much is this? 10 factorial, 5 factorial, 5 factorial, 13 factorial, 7 factorial, 6 factorial, times 12 factorial. Are those the same thing? Yes or no? That's a good, strong indication we thought correctly about it. Some other problems here. Here's an interesting one. I want to arrange 8 people at the table, at the round table. That is the next one. What was it? I don't know. Arrange 8 people at round table. Here are the chairs. So in how many ways? Obviously the people have IDs. Person 1, person 2, up to person 8. So I can put everybody in a chair, but the order matters. Matters who is in my left, who is in my right of the table. But if you rotate the whole table by 1 chair, you got the same arrangement, right? Whether the people sit, say 1, 2, 3, 4, 5, 6, 7, 8, or they sit, starts from here. 1, 2, 3, 4, 5, 6, 7, 8. Those are the same. It's the same arrangement. You're just looking at the table from the other corner of the room. These are not different arrangements, right? It only matters which is your neighbor, and you can see in those 2 pictures, 3 has the same exact neighbors. It just sits on a different chair. Chairs don't have IDs, so it doesn't matter which chair we see. How many ways are there to arrange people at the table? Yes.
7 factorial,
Why?
because 8 factorial would be the permutation.
So a factorial, he's saying that's the number of ways to arrange people on chairs,
But then there's 8,
but every arrangement has been counted
8 times.
8 times, because every arrangement can be rotated in 8 times to get the same exact arrangement, right? Pick any arrangement and rotate 1, 2, 3, up to 8. It's the same exact arrangement on the table, so we divide by 8. This is the number of rotations of the table. How can we think of this in a different way? Yes? Simpler way. I'm going to say me, one of the people, person 1, must sit on this chair. That's fixed. If he doesn't sit on that chair, I can rotate the table to make that person sit on that chair. So for person 1, there's no option. He sits on that particular chair. Now I'm done with the rotations of the table, because you can't rotate the table anymore if one person is nailed to one chair. Sorry. I mean to put it that way. But then, what are the options for the other 7 people?
You can put them in between other people or on the left or right side of another.
So there's 7 chairs for 7 people. It comes down in how many ways can you permute the other 7 to the rest of the chairs, because that one person won't move. Right? Okay, so that's the answer to that. How about this? I have this lattice here, 0, 0. It has m ticks this way, 1, 2, 3, up to m. And here, 1, 2, 3, up to n. And my purpose is to start from here, from 0, 0, and end in here. That's in mm coordinates. And I can travel either right or left. I can go left, left, right, left, left. Sorry, up, up and right. Right, 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 right. So I can go up and right moves. I have to get from 0, 0 to mn, which implies how many times I have to move to the right? M. So this would be m moves to the right, and how many times I have to move up? N. How many possible ways are from here to here that satisfy these constraints? Meaning they only go up and right. They don't go back left. They don't go back down. In how many ways can I traverse in here? How many paths? Paths can share edges, but they have to have at least a different point, right? They can't be, another path could be from here, I go first up, and then up again, and then I go here, and then I continue this way. That's okay, that's a different path. Yes?
Is it n plus m, choose n?
Correct, which is the same as m plus n, choose m. Why is that?
It's because you have n plus n.
Total moves, it's m plus n. The choice is which ones of those moves are
Going
up, or remaining ones are the ones that go to the right, right? Who's with me here? I have n plus n guaranteed moves, not more, not less. So you can think of them as a sequence of moves. The question is, out of these n plus n moves, which one goes up, which one goes to the right? Is any n can go up? Is there any n going up valid? Yes, because at any point, which I didn't reach up yet, total up, I can still go up. How about same problem. Same problem. Let's say from 0, 0 to mm this time. So I still have to go so same problem, but not allowed to cross the diagonal. So I can touch the diagonal, if I want to. I can go up to here, but I can't cross on the other side. So I'm asking, what are now the same problem? All the paths that go from 0, 0 to mm or mm, with one condition, mm to have a nice diagonal, right? The condition is the paths that go up in this side of the rectangle are not valid. You have to stick below the diagonal. Or you can touch the diagonal, just don't cross it. This is a very hard problem. This is PhD level problem. Just one small change, but I want to give you an idea to solve it. Okay? We're going to solve this problem, but we need an idea first. What is the number of putting parentheses? So what I mean by parentheses is here's for n equal 4, I can put parentheses this way. I can put parentheses this way. I can put parentheses this way, right? What else? I can do this, so on and so forth. So if I want to put parentheses, there is a rule of parentheses, right? You have to have more open than close. Any algebraic expression, see, when I get to this parenthesis that's a close, I can close because I have more open than close before it. Is this ways of putting parentheses effectively the same problem? Like this one? Every open parenthesis is a move to the right. Every closed parenthesis is a move up. By the time I get to mm, how many open parentheses I have? M. How many closed parentheses I have? M. Do I cross the diagonal? Why not? Because I always must have more open parentheses than closed parentheses. Doesn't mean the problem's easier, just means it's the same answer, but then how we check how many parentheses we can put 3 pairs versus how many ways are here to go. That's for Friday.
That's probably assuming you start with all the diagonal.
Yeah, starting 0, 0. So
Technically, can you first move is
you can touch the diagonal. No, that's not allowed. Using outside. You can touch the diagonal as many times as you want, but you cannot